welcome. Thank you for coming. I'm Nat Pryce. I work for Springer Nature, which is a scientific publisher, and we've been using Kotlin since it was in beta and started putting out our first production code into Kotlin when it first went into 1.0. And so we had a lot of Java programmers, and we had a lot of Java code. We converted Java systems into Kotlin. We started new systems in Kotlin. And I guess the sort of feeling as a long-time Java programmer approaching Kotlin was sort of something like this. Kotlin, and particularly the Kotlin type system, had a lot of unfamiliar concepts in it. What is a unit? What's nothing? What's any? What's a function type? What's a method type? What's a lambda? It was quite daunting to sort of come to Kotlin, fresh from Java. And also, I didn't find anywhere that put the Kotlin type system, which is really one of the selling points of the language, the whole sort of conceptual model of the type system, there's no documentation that brought it together into one place that let me understand how it all fit together. So I wrote a blog post about that, which turned out to be quite popular, and then this is really the talk of that blog post. Those of you who've read the blog post, there is more in this talk than is in the blog post. I'm also going to talk a bit about generics as well as a type hierarchy. But if you're coming from Java, quite new to Kotlin, I think the main message I want you to take away from this talk is don't panic, okay? Actually, the Kotlin type system is a lot simpler than that of Java. It has very few rules. It has very few special cases, if any. And the rules that do exist fit together very neatly and much more predictably than those of Java, allowing you to write code that's more consistent, that's more terse, more expressive, and allowing you to lean on the type system more effectively to prove the consistency of the code that you write and therefore avoid certain errors. So I'm going to walk through the Kotlin type hierarchy in this talk. But before I do so, I want to basically draw the distinction and define some terms, draw a distinction between types and classes, especially talking with people and answering comments on my blog and talking to other developers I'm working with. There certainly is some confusion from the Java side about what is a type and what is a class. So let's have a look at that. So both a type is an abstract concept that defines a set of values in an application or in a code base, and the operations that apply to them. Classes really define what those operations do, as well as how the data is stored by an object that is implementing that type. But the key difference to be drawn between types and classes is that a type is something that relates to an expression in the source code and not to something that exists at runtime. So types exist in the compiler and classes in the virtual machine. A slight oversimplification because of the way the JVM works, but fundamentally the key aspect of a type is it's relating to the syntax in your code and not to the actual values or objects sitting in the heap at runtime that expression, that piece of syntax actually refers to. So when you define a class that will exist at runtime, you also define a type that exists in the compiler to define the operations of that class, and that allows a type checker to check that you're using it correctly. But the relationships between types in the compiler and between classes at runtime are not always the same. And this can trip you up if you're coming from Java, especially if you most of the time you don't notice it, but you will notice it if you use reflection. Right? So when you use reflection and you're reflecting on the structure of your classes, those structures at runtime will be different from the relationships between types that the compiler is maintaining at compile time. The good thing about Kotlin that I find is that actually you don't need to use reflection very often. In our production code, we don't really use reflection at all. And therefore, we can make good use of the type system, and the fact that class relationships and type relationships are different doesn't affect our code. What is the value of being able to associate a type with a syntactic expression? We allow the type checker to prove properties of our code base, whether it's consistent or whether it's inconsistent, by analyzing the syntax alone without actually having to run up any code. So we get much more exhaustive checking of consistency than we would if we had to write unit tests. Again, it's not to say you shouldn't write unit tests, but we're able to actually, in our code base, write fewer unit tests in Kotlin than we would in Java because we can actually rely on the type checker to prove more properties of our code. But it's not just about detecting errors. Right? An IDE can point out mistakes in your code as you're typing it. IntelliJ is great for that. And also the auto-suggest, the refactoring, the autocomplete, the live templates can use the type system to generate code that is already consistent. So we can write correct code automatically using our IDE more effectively if our code is making better use of the type system. And this is a real problem that does exist. This graph up here is from a blog post by Rollbar, and it shows the top 10 JavaScript errors that their system detected in browsers at runtime, and 8 of those are type errors. Right? One of them is unknown script error. I'm being charitable in assuming there are no type errors in that bucket. JavaScript is an untyped language, and so type errors can easily creep through to runtime. But of course, on the JVM, if we use reflection, we end up having the same issue in that we're sort of working around the compile time type system and only detect consistency errors in our code at runtime. For example, the most commonly viewed question about Spring is why is a field that shouldn't be null at runtime? And that's a type error that we should be able to prevent at compile time. Right. Reflection, luckily in Kotlin, is needed. We find far less than we would rely on it in Java. And I think that's because Kotlin allows us to avoid the trade-off that we have in Java code between type safety and clarity. In Java, the sort of type declarations are very verbose. You get a lot of boilerplate. When you start to use sort of question mark super and question mark extends bits all over the place, it then gets very confusing all over your code. And so it's easier not to worry about it, to use reflection, because your logic is now clearer and easier to read. In Kotlin, we don't need to make that trade-off. I don't expect you to read this code here or to understand what it does, but this is an example. This is a piece of some of the HTTP routing from some of the microservices on the systems that I work on. And it's a combination of 3 libraries that make heavy use of static type safety. There's HTTP for K, which is, I believe there's going to be a talk about it maybe tomorrow or maybe later today. Crouton, which is type-safe routing and reverse routing for HTTP for K. And an early version of result for K, which is like a monadic either sort of a type, which is now being sort of made obsolete by Arrow. But the point I want to make is these make heavy use of the type system, so heavy, in fact, that an early version of Crouton would actually crash some versions of the Kotlin compiler because it was using types in such a crazy way. But the code itself has no type annotations in it at all. The type inference algorithm in the compiler and in the IDE checks the types for consistency, and I don't have to put in that code anything about the types that are used. They're exposed by the libraries, but in my application code, as I compose these things, the type checker can work without any additional annotations, and I can just focus on the declarative description of the logic that I want to actually perform. So let's have a look at the Kotlin type hierarchy, and I'll talk about how we use it, how we can make good use of it, some pitfalls along the way. It's not perfect. There are some things where it's easy to make mistakes, and I'll sort of talk about those and talk about what we do about them. Kotlin defines a number of built-in types, or intrinsic types, I think the documentation might call them, for numbers, booleans, characters. It defines some built-in structure types, arrays and strings. Some of these are defined in the standard library, but the compiler knows about them. So if I have a string literal, it's actually using a type defined in the standard library. It defines function types and then some sort of more unusual types, which is what we're going to talk about later in this talk, any and nothing and unit, which are quite unusual if you come from Java. And then you can define your own types by defining classes or interfaces or enums. And you can compose types into new types by defining function types, generic types, and using the nullable operator. Types in Kotlin are related to each other by subtyping. This is, if you know the solid, this is the Liskov substitutability principle, which is the L of solid. A subtype can be used anywhere, can pass to any code that can work with the supertype. In this example on the right here, if I have code that can work with fruit, I can pass it an apple. And one way of saying this is that an apple is a fruit. So that when you're talking about code and you're talking about the type model of your domain model with other programmers, you can say an apple is a fruit, and that is basically saying it's a subtype. It's the L of solid. So subtype relationships are introduced by subclassing, but they're also introduced, as we'll see, by generics and by nullability and other features of the language. So one thing to be aware of is that subtype relationships between types and subtype relationships and subclass relationships are not always the same. So particularly with generics, but also with interfaces. But again, you'll only notice that if you're using reflection, and thankfully in Kotlin, we don't need to use reflection very often. I might be saying that quite a lot in this talk. And subtyping is transitive, so if I have a subtype of a subtype, then it also is a member of the supertype. So in this case, an apple is a pippin is a kind of apple, and therefore it's a kind of fruit, because apple is a kind of fruit as well. So now, I have to be very careful about terminology here. So the type of the root of the class hierarchy in Kotlin is called any. And the compiler magically translates that into Java Lang object when you're running on the JVM platform, but hides that mapping from you in most cases, unless you're using reflection. So it's the equivalent of object in Java, except that it's not null. We'll look at nullability later. And all classes in the system are either direct or indirect subtypes of any. But any doesn't really provide any useful operations on it. Interfaces are also subtypes of any. Now, this is where the runtime class structures and types start to differ markedly. If you reflect on an interface class, you'll see that if you ask for its superclass, it will be null. If you ask for its superinterfaces of an interface with no direct superinterface, it will be null. But the compiler allows you to pass an interface anywhere that an any is expected, because every interface is a subtype of any. So that, again, until you use reflection, you don't notice this. As long as you never use reflection, you'll never notice this, and the type checker will do the work for you. And any doesn't have any useful operations on it, really. So if you are passing around values of type any, you're going to have to cast it to actually invoke any useful operations on it. And at that point, the compiler, most of the time, will not be able to help you check that cast. So it's up to you to get it right. It's a source of bugs. So we can, it won't check that the cast is correct, and it also won't check that if you're building a class hierarchy, you're adding subclasses, that you're casting from a superclass down to a subclass is going to cover all the cases. So we can avoid this problem by either programming to interfaces as we do in Java. So we don't care what the actual class is. We just know that we're passing in a value that implements a particular interface and therefore has a particular type, and the operation is on that type. Or we can use a sealed class hierarchy to sort of lock down an area of the class hierarchy to guarantee to the compiler that there will be no more subclasses added in the program, and then the compiler can exhaustively check if statements that are using is to look at the particular types that are being passed in and casting. Patrick Cousins is going to be talking about seal class hierarchies tomorrow, and so I'm not going to say any more of them about them, but I do recommend you go and see his talk about that. So unlike Java, Kotlin doesn't have a void type. Void in Java is a strange edge case, causes a lot of duplicate code. So for example, Java has a runnable interface for tasks that do something but don't return a value, and a callable interface for tasks that do something and do return a value. In Kotlin, functions that have side effects but don't actually calculate anything do still return a value. They return a value of type unit. And unit is a type with only one value, also called unit. There's nothing special about it. It's just an object that's called unit and is defined in the standard library. You can define your own types like that if you want to. And so the compiler, just if you don't put a return type on your function, and therefore the function is only being used for its side effects, will implicitly type that as unit. And it will actually return you a value of unit if you call it. So most of the time, you don't really need to use a unit type. There's no, yeah. So yeah, that's the actual definition of unit from the standard library. So you can see it is just plain Java, Kotlin code. There's nothing special about it. Now this is an aspect of the Kotlin type system that has no equivalent concept in Java at all, the type nothing. So the type nothing is used for expressions that don't produce a value at all. Type unit is for expressions that complete but only perform side effects, and they will return, but they won't calculate anything, but they will return back to the caller. The type nothing is a type that has no values in it. It's the empty set. And it represents the value of an expression that never completes. Right? So, and this is different from null as well. So null is also a value that only has one value in it that can be returned. But you can get null by getting a value out of an expression, but nothing, the expression won't actually return back to you. Right? Which means that any code following an expression of type nothing is guaranteed to be unreachable. And the compiler will warn you if you try and write some code after an expression of type nothing. So what kind of expressions evaluate to nothing? Well, those that perform control flow. So here's some examples. So the throw expression is an expression that throws an exception and just immediately interrupts the evaluation of an expression, but is itself an expression of type nothing because it never actually produces a value. And we can, because nothing is the ultimate subtype of all types, I can include an expression of type nothing in an expression that will actually calculate some other type. In the first example up here, I'm calculating an expression of type int, and one of the branches is throwing, and therefore has a type of type nothing, but it's okay to include a type of type nothing in an expression of type int. And so that will perform a calculation if the number of glasses sold is greater than 0, or throw. For a Java programmer, what is quite surprising is that the return statement is not a statement like in Java, but it's actually an expression as well. It's an expression of type nothing because it interrupts the calculation of an expression and immediately returns a value out of the enclosing function. So in the second example on this slide, I have, instead of throwing an exception, I'm returning a string from the function because the function is declared to return values of type string, and I can return that string from within an expression of type int because the return expression itself has type nothing and also performs some control flow to interrupt execution of that expression. So is this idiomatic Kotlin? I was having a somewhat acrimonious discussion about this with my colleague. I'm saying, yeah, this is quite idiomatic Kotlin. We do this quite a lot. to simplify otherwise nested if statements. His opinion was, it's not idiomatic. Don't show people that at all, please. It's up to you. Use it as you see fit. With great power comes great responsibility. The other great thing about nothing, of course, though, is we can write our own control flow structures in Kotlin that evaluate to nothing. I can write, for example, a control flow structure that runs an infinite loop. That infinite loop will never return. And so I can declare it as having type nothing. And then my control flow structure interacts with the unreachable code analysis provided by the IDE and the compiler. Because the unreachable code analysis is not based on special cases like it has to be in Java. In Java, you have to know throw can cause unreachable code, and return can cause unreachable code, and system.exit can cause unreachable code, and so can interrupting a thread or whatever, right? All of these things have to be special cased in the compiler. In the Kotlin language, we just say that our function returns nothing, and that drives the unreachable code analysis, and we can then plug our own functions into that. And in the standard library, you can see this used quite frequently. The function to exit the process returns nothing, as does the to-do function. The to-do function is just a function that returns nothing, that evaluates to nothing and throws an illegal argument exception or some runtime exception. But because nothing is the very root of the type hierarchy, it's included as an element of every type in the system. There's no way to express in the type system that an expression will not fail, right? Which I guess is just pragmatic, right? It's like things fail, right? Our system might just get turned off. It might run out of memory, might call a library function that blows the stack. We might have messed up our packaging of our application, and it will run into some code, and the class will be not on the class path, and you'll just get a link exception. So, yeah, you can't declare that something can't fail in Kotlin. So far, I've not talked about nulls, but I think, coming from Java, the null safety in Kotlin is one of its biggest selling points. Certainly, it's the easiest selling point for selling like Kotlin to teams of Java programmers and sort of encouraging them to adopt it. I think it's what gives Kotlin its biggest bang for the buck. It's fantastic. And it probably won't surprise you to hear that subtyping also underpins how Kotlin performs the type checking of nulls and null safety. So if we create a type hierarchy, here's some fruit, an apple can be a fruit, an orange can be a fruit. We can define nullable versions of those types by putting the question mark at the end. I don't know how you meant to pronounce that. I've been sort of pronouncing it. I've tried to pronounce it in an Australian accent, so it's like I've got either an apple or an apple. But it's, yeah, so I might just start saying apple question mark to mean nullable apple, or maybe I'll say nullable apple, I don't know. One of the more awkward parts of the language is how do we talk about types that have just a sort of funny sigil at the end there. So if I define my type hierarchy, the nullable aspects of that create a parallel type hierarchy that mirrors the type hierarchy I've defined, which kind of makes sense. If I've got some code that can work with any kind of fruit, it kind of makes sense that code that can work with a sort of optional, possibly missing value of any kind of fruit can also work with a possibly missing apple or a possibly missing orange. What's not obvious, but I think it's really cunning, is that nullability itself is represented as a subtyping relationship. So I automatically generated these diagrams, which means that they didn't lay themselves out entirely as I'd have liked. But if I sort of animate them back and forward, you can kind of see, hopefully, maybe not, that there is a subtype relationship and supertype relationship between the non-nullable and the nullable types. That is that the nullable type is a supertype of the non-nullable type. That makes perfect sense. If I've got code that can deal with a possibly missing fruit, I can pass a fruit, an actual fruit in, and it should work fine. If I've got code that can only work with a fruit and can't deal with missing fruit, I can't pass a missing fruit in there, right? I can't pass null in there. And that just falls out of the subtype relationships being checked by the type hierarchy. Null safety is not a special case in the language, it just falls out of the standard null, the subtyping relationships that the type checker is working with. However, again, these subtype relationships, they're not visible at runtime. Right? If you're trying to reflect on these things, you're not going to be able to see them in reflection. Luckily, we don't need to use reflection very much in Kotlin. There are a couple of subtleties. You can't have an option of an option in this model. The supertype of a nullable type is itself, or rather, if you put question mark, question mark, question mark, question mark, that's exactly the same as just putting one question mark. So you can't, it's not like you have an option type in, like in Java, where you could have an option of a fruit. You can only have an option of fruit. There's also no way to say that a function is only applicable to nullable types, because the non-nullable type is a subtype of the nullable type, so you can't limit a function to only work on nullable types, because it will also work on non-nullable types. There are a few places where there's code that sort of by default works on nullable types, and when you pass in you can get some sort of weird effects. The toString on any question mark can return the string null when you pass it null, and sometimes you want it to return a null, not a... Anyway. So what this means, though, is that any doesn't actually mean any value. Okay? I made this mistake. I released a library called Hamcrest for testing, and I wrote a predicate in there called anything, which was defined to be part, you can just pass any to it, but it didn't, it should have just taken any value. But it didn't work with null, because null, any doesn't include null. So actually, if you want to say any value, you have to say any question mark, and that includes null as well. Not much of a problem within one code base, because you can just change it and recompile. But if you publish a library, something you have to be careful about. Unit can be nullable. Right? This just falls out of the fact that the type hierarchy is consistently applied. Kotlin's type system doesn't have special cases like void, but I've not actually found any use for a nullable unit. But if you do have code that works with generic higher order functions, and you pass in a procedure that returns unit, it will work perfectly fine with it, because unit is a value that can be passed around. It's not a special case like void in Java. Right? But usually the standard library has better ways of doing things. You could map a procedure over a collection, and you'd end up with a collection of references to the unit singleton, but it's probably better to use a library feature like for each to perform something and not cause, create a load of garbage. And then at the bottom here is a strange type, nothing question mark. So nothing is the type that has no values. Nothing question mark is the type, at type, or null. Right? So this has no values or null. It can only have one value, which is the value null. So actually, nothing question mark is the type of null. You can actually find that out by exploring it in IntelliJ and asking it for the type of a value an expression that evaluates to null. And this is actually surprisingly useful. So if you have nullable types, you can accidentally create overload ambiguity. So here is a little bit of a sort of internal DSL to create JSON structures. And I can create a string property by saying x of 10 or y of null. But when I say y of null, the compiler doesn't know which of the two of functions on the left there I'm intending to call, because null is a possible value of both nullable int and nullable string. There's nothing a compiler can do. But I can solve the problem by providing an overload specifically for the null literal, because I know that the type of the null literal is nothing question mark. I add that in, provide an appropriate implementation, and my overload ambiguity error goes away. One sort of syntactic weirdness is that in generics, although we don't put a question mark at the end of a generic type parameter, that generic type parameter is actually nullable. If we want to, so for example, in the list of function in the standard library, I can pass nulls to that list, to that function, and get a list with some possible nulls in it. So if I want to say that a generic type parameter cannot be null, I have to declare that it must be a subtype of any. So, for example, in the function at the bottom, also from the standard library, here it declares that t must be any, therefore t cannot be null. Passing in an iterable of t question mark, therefore the iterable that's being passed in could contain nulls. Filters out null, returning a list of t which cannot be null. So the non-nullness of the return value is declared by the type system, and after calling it, the type system knows I don't have to check for nulls in any of the values of the list that gets returned. All right, so we've looked at the sort of class hierarchy. So let's have a look at generics, since that's another important part of the type system and is widely used in sort of domain modeling. So again, we'll probably talk about, it won't surprise you, that generics also involves a lot of subtyping. That's the fundamental sort of conceptual model to get your head around in Kotlin. But first, let's take a quick detour to talk about what is a generic. So a generic is itself not a type. Okay? It's best to think about it like a function that, given a type, will create a new type. So box isn't a type, but a box of fruit is a type, and a box of orange is a type. Although box does create a class. Box of fruit doesn't have its own class. Box of orange doesn't have its own class, at least on the JVM. But box has a class. So again, the relationships between types and classes, not the same, only visible when you use reflection, and we don't need to use reflection very often in Kotlin. If I define a class hierarchy of items to pass to a generic, so that'll be used as parameters of a generic type, by default, the generic type will have no subtyping relationships between the instantiations of that type. So if an apple and orange are both kinds of fruit, a box of fruit is not a box of apples is not a box of fruit. Kind of makes sense. If I've got a box of apples and I treat it like a box of fruit, I can put some bananas or oranges in it. Someone else using it as a box of apples will suddenly find it's got unexpected types of items in it, and vice versa. So, and it's particularly because items can be put in and out of this collection. If we want to create subtyping relationships between instantiations of our generic types, we have to use variance declarations on the type itself, on the generic type. And they get a bit mind-bending. So I'm going to use the term output variance and input variance, although Kotlin uses a term in and out for the variance keywords. Invariance and invariance sound too similar when you're speaking. So input variance and output variance are an easier thing to talk about. Output variance is where you're declaring that the generic type will return to the caller items of the type parameter. So a supplier of fruit will return values of fruit when I invoke its receive method. A supplier of apples will only provide apples. And because I've set the out variance on the generic type there at the top, Kotlin will produce subtyping relationships between the instantiations of this generic type that follow the subtype relationships of the item type. So if I've got, I don't know, a juice bar, and I can juice all sorts of kinds of fruit, I can receive fruit from a supplier of apples just as well as I can receive fruit from a supplier of all different kinds of fruit. Subtype, because apple is a kind of fruit, I can process individual apples, therefore I can plug a supplier of apples into my juice bar of fruit. Input variance works the other way. So input variances, you declare that the generic type will consume or be passed values of the parameterized type. And Kotlin will produce subtyping relationships between the instantiated generics that are the opposite way round from the subtyping relationships of the elements of the generic. So as you add more subtypes to the element or to the parameter type, you get more supertypes of the generic type. It's kind of a bit weird to get your head around, but it does make sense. If I've got in my juice bar, this is a juicer I've got at home. Here's a juicer that I normally have in a juice bar. I've got a juicer of oranges, and I've got a lot of oranges. I can put oranges into my juicer of orange. If it breaks, I can use a juicer that can accept any kind of fruit and put my oranges into it. Right? I couldn't do it the other way around because putting pineapples into a juicer of orange would jam the mechanism. Yeah, maybe it's a bit of a stretched metaphor. But the great thing about having type inference and a type checker as convenient as Kotlin is the computer is doing it for you. Right? You don't have to get your head around the fact that as I add subclasses, I get new supertypes of my generic type. The type system is ensuring that we're plugging the components of our systems together in a way that is consistent and safe according to the rules of subtyping. But you have to be explicit about these variance declarations. The compiler won't infer them for you and then infer subtyping relationships between the instantiations of your generics. So here I've got a hopper, which could have output variance, right? Because I'm able to take things out of the hopper, and I've got an automatic juicer that I can put a hopper into, and it wants a hopper of fruit. But I can't pass a hopper of apple in. Even that kind of makes sense because I've not declared output variance on the type, on the generic. So again, in your own code base, not a problem. As soon as you find the error, you can fix it. But if you're publishing libraries, this is something you have to be aware of and be careful about. And luckily, IntelliJ can give you hints that you could add output variance or input variance onto this generic if it notices that the parameter type is only ever returned from functions of the interface or passed into functions of the interface. So one sort of stylistic convention that is both in the standard library and is very useful to ensure the maximum flexibility of your code is to separate out types that can have input variance and types that can have output variance and types that are both read-write and therefore can have no variance. You can see this. So here I've got two interfaces, the source of something, it's got output variance. Is that right? Yeah. The source of something and output variance, I can take things from it. And a store of something that's got input variance, I can put things in. And then I can define box, which has no variance, as both a store and a source. And I can pass it around as a store, and I can pass it around as a source, and the variance will be taken into account. The subtyping relationships automatically constructed by the compiler will be taken into account effectively. We see this in the standard library, where it makes a distinction between list and mutable list, or set and mutable set, for this very reason. So you can pass around lists of T's which have output variance, and the subtyping relationship just works as you would expect. So that was kind of a whirlwind tour of quite a complicated subject, and hopefully that's given you an understanding that Kotlin's type system, although it has a lot of features, a lot of really useful features that can be, we can really lean on to model your domain effectively and check your code effectively and work well with the IDE's support for refactoring and auto-suggestion, is actually based on very few fundamental ideas. It's based on subtyping. It's based on the fact that nullability is a kind of subtyping. And it's based on the fact that input and output variance of generics is also a kind of subtyping. And that's it. And any at the top, nothing at the bottom. So subtyping, awesome. Hopefully, that would be useful information for people coming from Java to Kotlin, as it was for me and other people that I work with. Thank you very much.